Okay, so moving on, we now have the distinguished speaker, Dr. Ian Young, from Senior Fellow from Intel. So I had hard time compressing his bio. His bio is so impressive. But anyways, he will be presenting a talk and an IC designer's perspective, embracing technology changes with innovation around its constraints. Let me read his bio. I'll try to compress it down. He joined Intel Corporation in 1983, starting with the development of the circuits in the world's first 1 megabit CMOS DRAM, first 1 micrometer 64 kilobit SRAM. Then he led the design of 3 generations of SRAM products and developed the first generation of analog PLL-based clock generator circuit on microprocessors. And also, he had subsequently developed core PLL clocking circuit building blocks using each generation of Intel microprocessors through Pentium 4. And from 2001 to 2010, he led a circuit design team doing the research and development of analog digital mixed signal high-speed serial IOs for microprocessors, wireless RF CMOS synthesizers, and etc. He has authored or co-authored more than 300 technical papers and holds over 250 US patents. And he has received numerous awards, including 3 Intel Achievement Awards, 2009 ISSCC Jack Raper Award for Outstanding Technology Direction Paper, 2018 IEEE Frederick Phillips Award, right? And he was the TPC chair of ISSCC in 2005, as well as the symposium chair for VLSI Symposium in 1997 and 1998. Okay, I have to cut down here. So Dr. Young, the floor is yours, please.
Thank you, Gerald. Thank you. Thank you very much for the introduction, and it's really a pleasure for me to be here. I hope you can hear me, everyone at the back. Yeah, it's my pleasure here to give this talk today. I was asked to give some talk to new, inspiring integrated circuit designers. And as you know, as from a bio, I've spent 40 years, more than 40 years doing integrated circuit design, and so it's my pleasure to give you some of that perspective. So this is the title of my talk, as was in your outline, as in your digest. So integrated circuit technology, in the beginning, it started with the planar transistor. So many of you know that the transistor was invented at Bell Labs in 1947, but it took 12 years for the real manufacturable bipolar transistor to be processed and manufactured, and that was done in 1959 at Fairchild, and that was the planar transistor, and the whole industry copied this planar transistor technology. At the same time, a short time after that, that was, by the way, Dr. Herney was the one who patented that invention. It was followed by Bob Noyce, who came up with the idea of using the silicon dioxide that passivated the bipolar planar transistor to run metal aluminum wires over the top and interconnect multiple transistors. And that became the very first integrated circuit. You can see on the right here, the first integrated circuit, one of the first integrated circuits was a 4-transistor flip-flop with 2 resistors. Now, this is what, at this time, Fairchild was started. Herney was one of the founders. Robert Noyce was a founder, and also Gordon Moore was a founder. And he was a director of the R&D group that came up with these technologies. So it's very important that you realize that Gordon was right there at the very beginning. He was a chemist, and he did the double diffusion technology. Okay, so I keep going backwards. At that time, just within a few years, in 1962 and 1965, he started to look at the number of transistors that were able to be made and yield on an integrated circuit. And he found that the cost per transistor was going down when you put more transistors on that one piece of silicon. And that was what inspired him to write a predictive a prediction of what it would be like in 10 years. And that was what is on the right-hand side of the bottom, on the right-hand side of the slide, shows his prediction of how many transistors there would be on an integrated circuit in 1975. So when he predicted, there was only 64 transistors on integrated circuits. And of course, he projected further out, and by that time, it was going to be over 1,000 transistors. And this was a doubling every 1 year. But in 1975, he changed his law to doubling every 2 years. And he has a reason for that. There's a reference at the end of my talk that you can read about that history. So now, what happened to his prediction? Well, he was predicting that the cost per transistor would go down, and this is what drove, from an economic point of view, and motivated people to improve the defect sensitivity on the chip. And so we've gone through a period of exponential growth in number of transistors, and we've been going for more than 50 years, 55 years, in fact. And there was a golden era where we had this Dennard scaling. Many of you read in your classes or hear in your lectures about Dennard scaling. That was where we simply scaled channel length, thicknesses of dielectrics, and voltages. But around 2003, there was a change where the power density was so high, the power consumption was so high, we had to make a change in the way microprocessors and large-scale integrated circuits were designed, and we had to go to parallel cores. And so that's why single-threaded performance, even though transistors were going up exponentially, Moore's law continued, we slowed down the frequency. The frequency increase plateaued at around 3 gigahertz, and then the single-threaded performance had to go to parallel throughput. And so we saw the number of cores go up. And so today we're going to hundreds of cores on the chip. But meanwhile, Moore's law continues. The invention of scaling the transistor down continues, and I'm going to talk about that. So this is what's happened. So remember, I started out when I talked talking about the first transistor, the planar transistor was a bipolar transistor. The first integrated circuit was a flip-flop bipolar transistor integrated circuit. But 10 years after, in 1968, Robert Noyce and Gordon Moore decided to leave Fairchild and to go to a company they started called Intel. And there they founded a company to build MOS transistors, MOS integrated circuits using the silicon gate. And the MOSFET transistor has been what's been the scaling of transistors ever since, for over 40 years. And so we've gone through many technologies. We've gone from NMOS circuits to CMOS circuits. And why did we make the change? Because of power density, power consumption. We've also had to go through interconnect transitions. And so we've gone from aluminum to copper. And then when Dennard scaling ended, we had to go to other techniques beyond Dennard scaling. We had to use strain to improve the mobility, high K metal gate to be able to attack the leakage current in gate oxides, and then the FinFET. And I'm going to talk a little bit more about the FinFET in the next slides. The FinFET technology was rather unique. So here's some of the transistor technologies that occurred after Dennard scaling ended, but Moore's law continued, scaling continued. Mobility was improved by strain. High K metal gate reduced the gate oxide leakage. FinFET, it enabled us to build a shorter channel length because we had better electrostatics. So thus we were able to have a shorter channel length and have higher density in the transistor gate circuits. And in fact, we took what was a planar transistor, and for the first time we deviated from planar and we went into the third dimension where we went up vertically and we got higher width of transistor in a small area. So in fact, that reduced the area of our logic gates. And subsequently, we've gone into improving the channel mobility of PFETs. So this is example of what happened to the standard cell layouts with FinFETs. The vertical dimension, the vertical dimension here, the cell height got reduced down because we increased the surface area by going up over a fin, and thus collapsed down the vertical silicon area on the chip. So we were able to do vertical scaling in the layout. We were able to do horizontal scaling because of the short channel. We could reduce the channel length. And of course, I just want to make a note for analog circuit designers. It was feared that FinFETs would be harmful to, difficult for analog circuits. But in fact, because of the better short channel effect, effect, the better our output impedance of the transistor, better GM of the transistor, we got higher performance, GMR out, higher FT, higher Fmax. So following the FinFET, we're now moving into the era of the nanoribbon. And so this is what's called the GAA is called gate-all-around ribbon FET. And its value proposition is similar to the FinFET, but it allows us to further scale the channel length of the transistor because of the electrostatics. So it has some benefits from that point of view. We can have a shorter channel length and get more drive current per unit width. In addition, we stack these nanoribbons vertically on top. Instead of having a FinFET that's vertical, we now have ribbons, basically fins that are horizontal, and we stack them up in layers. And we can thus reduce the area to get a given drive current of the silicon. So once again, reducing the area that takes for these logic gates or analog circuits, reduce the wiring, help the dynamic capacitance, and so forth. So this is the next step in improvements of transistor scaling. Let's look at interconnect. Now, many of you know we must not forget about the interconnect. That's part of the integrated circuit, the parasitics of the interconnect, the resistance of the interconnect. So what has happened with the industry, they've continued to do scaling of the pitch of the wiring, and that's continued down according to the Moore's law, the 0.7x every 2 years. But however, we've also increased the number of layers of interconnect to get those wires that are needed to interconnect those transistors and those gates. In fact, this is very much predicted. Now, remember, we're doubling the number of transistors every 2 years, but we're more than doubling the number of microns of wiring that we need for those transistors. And for those of you who want to look it up, it's Rent's rule. This is a higher exponent and then a squaring, a doubling. So we need to have more wires as we put more gates on the chip. And hence, we started out in 1 micron process technology with one metal layer and 1 polysilicon. And today's advanced technologies at the 3 nanometer node, we've got 16 plus metal layers. And this is some visual cross sections of some of the interconnect history over the time. With low-K dielectrics, and we went to copper around the 2001 timeframe. We left aluminum behind, and we went to low-K dielectrics and copper, and we had 6 layers of metal. Then in 2014, we were at 12 layers of metal, and we used pitch halving to get the scaling of the wires. 13 layers of metal in 2019. With quad patterning. And today, in this year, 2024, you'll see a technology introduced from Intel called PowerVia, where we're now not just got the 16 layers of metal signaling on the front side of the wafer, but on the back side of the wafer, we're going to bring in power. It's called PowerVia. We're going to have the power distribution on the back side of the wafer, and this will reduce the IR drop of the power distribution, the losses in the power, and managing the transient noise on the chip. So this is an example of a visual of backside power. In the beginning, we were always doing power delivery from the front side, okay? And so we have the transistors. You can't even see the transistors down here, but we go all the way up here, and the coarse redistribution layers of metal at the very top. So we've got like 16 signaling layers and about 3 redistribution layers. So signal and power were on top of the silicon. But now with backside power delivery, you're going to have the signaling on the front side and the power and the bumping of the die from the backside. And this then reduces all of the losses in getting power into the transistors, which are right down in here. And you can see it as this. So it provides more efficient power distribution, enables either relaxed metal zero pitch, a simpler process, lower cost, and better utilization and better performance. So even looking to the future, we're looking at chiplets, and many of you may have heard about multi-chip packaging. So this is the evolution of Moore's law, where we're dividing down the chips into technology-centric, optimized technology for that given compute or analog function, and putting it into a 3-dimensional package. And so it could be interconnected with it's an SoC, and it could be interconnected with a base tile substrate with smaller tiles on top of it with a package. And one of the technologies that Intel's using is Foveros, where we got a silicon die with high density interconnect between the two die and the package underneath. So what's the future beyond nanoribbons? Well, we're going to have stacking of these nanoribbons. So CMOS will now go even more 3D, where the N and the P channel transistors, even though they're nanoribbons or nanowires, they'll be built on top of each other. So we're taking the CMOS inverters, N and P, we've now got them one on top of the other. And then longer term, we're looking at further scaling of the transistor to two-dimensional materials, transition metal dichalcogenides, what's called 2D materials, and they'll enable a shorter channel length down into the sub 5 nanometer region. That's in research. Now, I've talked about the innovations in the transistors, and as those of you who read the title of my presentation, you'll hear it's about innovation in circuit design. So we've had these evolutions of transistor technology and interconnect, but we've also had evolutions in circuit design. And I wanted to give you a little bit of the history of that. So first of all, this is a big picture of the history of integrated circuits going back just to 1961. Earlier than that, we're talking about the era of the bipolar transistor, but the microprocessor was developed and invented, first introduced in 1971, the 4004, with 2,000 transistors. And so evolution, we started off with NMOS. Then we went to CMOS fairly quickly because of power and with 2 layers of metal. That was 1 micron, 3D6. The 46, they added the floating point processor to the microprocessor, and also they had on-chip clock distribution, generation and distribution. Then the Pentium added out-of-order execution, and we also added another transistor to the technology to have more drivability, called BiCMOS. It was a very simple addition of a single NPN transistor to help the pull-up of the PMOS, and this transition gave us effectively a half a generation improvement in performance. Pentium was a superscalar pipeline. Integrated graphics was added to the microprocessor. We went into that era where we had to do parallel processing because of the power consumption. We used multi-core processing and dynamic voltage frequency scaling and power gating, very analogish circuits here. We then went into integrated chip-to-chip interconnect, QPI, which was a bus to communicate between one processor and another processor, PCI Express for peripherals, DDR for memories, high-speed serial IOs that are going very, very high gigahertz, tens of gigatransfers per second, and these are very analog intensive. Heterogeneous chiplet packaging, I introduced that to you. And then recently, we're now talking about AI accelerators. Artificial intelligence is growing dramatically in the amount of performance it needs. And so integration and accelerator design is now very much the focus. But I want to give you a little bit more about the circuit innovation. I've given you some of the architecture innovation in that history, timeline history, and I've given you some of the circuit innovation in that history too. But I just want to dig down a little bit more on some of those analog mixed signal circuits. Computing has to have analog circuitry on it. Integrated analog functions have enabled the compute performance to scale. Without integrated analog functions, computing would not scale. For example, if you look at a microprocessor today, we've got voltage regulators integrated, we've got all this high-speed serial I/O, we've got die-to-die, you've got the clock distribution, multiple cores with their individual clock generators and so forth. So let's just go back. What happened over that history? Well, back, as I said, in the early 70s, the bipolar transistor was the way analog circuits were designed. But then at Berkeley, they saw the MOS integrated circuit growing enormously, memory design, microprocessor design, so many transistors. So they saw that the future was going to be that we need to build analog and coexist it with digital MOS transistors. So they started to look into research for doing analog MOS in integrated circuits. And of course, this was a paper in 1975 and by Berkeley, and of course their prediction has come borne fruit in very many multiple times. So without this, we wouldn't be able to have scaled. And they went into the analog op-amp and the switch capacitor filters and A to D converters. And of course, the rest is history, where we wouldn't be doing high-speed serial I/O today without the analog MOS. So this is the phase lock loop. It was introduced to the 486 because there was so much clock loading for all the flip-flops on the die that there was too much clock buffer delay on the chip. So we needed really to have a big buffer without any delay. We wouldn't be able to implement the setup and hold time for the flip-flops with so much delay in the clock distribution. So a PLL was introduced to the microprocessor. First analog circuit, really very sensitive analog circuit, introduced the microprocessor, and it had 0 delay. And it had another advantage. It enabled you to multiply the clock frequency. So we could keep an external clock of like 25 or 50 megahertz and multiply up the frequency. And today, with the 50 megahertz clock, we multiply it up to 5 gigahertz frequency. So wireline occurred, and in 2008, we were using just a front side bus for all the IOs, but then we introduced this high-speed serial point-to-point communication called QPI, it was called. That was between processor and processor, and PCI Express and DDR. And here's some examples of multi-core processors that had these PCI Express and QPI on them. So your future, what is your future? Just like the innovations over the past 50 years, transistor technology changed, circuit technology changed, more integration, Moore's law enabling more integration, so more system-on-a-chip functions came together, heterogeneous cores, heterogeneous application-specific cores, and so forth. So the integrated circuit designers will make an impact in the next 50 years, just like I believe they will make it in the next 40, 50 years, because they've done it in the past. Circuit design and architecture and innovations will be required. So you, entering your careers over the next 30 years, you will have these changes occurring. I encourage you to tackle these changes. They will be challenging, but keep up your skills up to date and continuously learn. Understand the technology. It's a co-design of what the process can do and what circuit design can do. Analog circuits, digital assistance from analog circuits, it's co-design. So I got a couple of slides to give you a little bit of thought about what would your career look like in the next 10, 20, and even 30 years. We have a computing energy efficiency problem. The power consumption of our computing consumption is growing, it's getting exponentially climbing, and it's getting to be approaching the amount of power generation in the world. This is unsustainable. It will slow down the amount of performance that we get from computing unless we do something about it, and that means we have to come up with a new technology, integrated circuit hardware, that will be more energy efficient to break this plateauing and saturation point. Is there a new hardware platform? Well, my group at Intel, and I think a lot of universities around the world, are looking at a transistor that could be beyond CMOS, be more energy efficient. We are also looking at non-traditional compute, something that's maybe more analog in compute, and maybe more brain-inspired. Remember the history, I've given it to you. Bipolar circuits were the beginning of the integrated circuit. They were for digital, they made logic gates, they were for analog, made amplifiers, analog circuits. But power dissipation was the problem, so we went to CMOS. And we've had 40 years of CMOS. And now the question is, we've got a power problem again. So what are we going to do? So we've faced this before with the CMOS, so maybe we're going to have to come up with a new transistor technology in the future. So lastly, some points to make about analog compute, non-traditional compute. Maybe there are new devices with variability in them, such as the probability bit, the p-bit. Circuits that are based on ring oscillators, arrays of ring oscillators, synchronization, Ising computers, and also algorithms. All of these are needed to attack some of these exponentially hard problems that quantum computing is tackling, but probably maybe can be done in room temperature new hardware platforms. embracing new algorithms. So combinatorial optimization being one of the challenging compute problems of the future. So I've gone over time, but thank you very much for your attention and your patience. I have some extra homework reading for you, some references there on the Gordon Moore's journey. You'll look at some of that history of the integrated circuit, and also some futuristic paper on the benchmarking of beyond CMOS. So thank you for your attention.